Welcome. If you look at duality for polyhedra, you can start with a nice manifold like the icosahedron, right? Every unit sphere is a circular graph. Then the dual space is no more a manifold, right? So you have to refine it. You have to produce a stellation here to get to a manifold. Especially in higher dimensions, this is crucial that we have a nice notion of duality, and it's no problem for two-dimensional polyhedra, right? We know what the faces are, and Lakatos has kind of shown how much confusion mathematicians had over the centuries with defining what the polyhedron is. So for me, I mean, I'm working on graph theory, and we have a nice, object and graph, a finite simple graph, and we can look at the simplices complex defined by it, which is given by the complete subgraphs. And the barycentric refinement is just a graph of that simplices complex. Two simplices are connected if one is contained in the other. So this is a nice notion. You can iterate it and you get to a nice barycentric limit theorem, central limit theorem there. If you look at spectra like the Hodge Laplacian or the Kirchhoff Laplacian, which is the zero, then part of the Hodge Laplacian, or the connection Laplacian, what happens is if you take the limit, you get to a universal law. I mean, the density of states converges, like in the central limit theorem, in law to a measure which is defined when you have the maximal dimension. It only depends on the maximal dimension. That's a very nice notion. I worked on this in 2015, now 9 years ago, and it's almost too simple to be published because it's essentially just a linear algebra result. I'm using the Lidsky last theorem, which I learned when I was at Caltech from Yoram Last. He generalized, kind of made Lidsky's theorem nicer, and I love this version of Last, which estimates the sum of the absolute values of the eigenvalues of a matrix in terms of the matrix element. Very handy, right, in graph theory, because if you want to compare two graphs, now we can compare the spectra. And so what happens with barycentric refinement, you kind of split the space up, and then there is a boundary part which is neglectable in the limit because the boundary part grows slower. So they grow exponentially, like 6 times in 2 dimensions, 24 times every time you make the refinement in 3 dimensions, n factorial, d factorial in dimension d. So that is this barycentric refinement. Now duality, when you look at duality, and I was looking at this in 2016, 2015, 2016, you don't want to have the full barycentric refinement. You want to have something which is kind of closer to the duality. What is the dual graph of that? The dual graph is actually just, you take the faces as your vertices and you connect to if they intersect, and then you get back that. So you have this duality, but what happens here, this is not triangulated, so you have to triangulate it. If you want to triangulate it, that turned out to be the right notion. It's a notion which works in arbitrary dimension, preserves manifolds, and I call it the soft barycentric refinement because it is less hard, right? What happens in 2 dimensions, the vertex degree does not explode like in the barycentric refinement, but it stays bounded. So it looks a little bit like this. If you start refining this a lot, you get polyhedra like that. That's very nice for computer graphics, for example, because you don't want to have this, large degree vertices which have very negative curvature degrees. So the example which I kind of like very much also in higher dimensions, you take an octahedron or higher dimensional octahedron and you apply that, and then you get the stellated cube. In 3 dimensions you get the stellation of the tesseract. And the tesseract is one of the most famous objects in mathematics. It's the 3-dimensional sphere, kind of a 3-dimensional sphere if you take the faces as a cellular complex, but it is a 1-dimensional graph because it doesn't have triangles, so you have to triangulate it. And how do you triangulate it? the best way to do that is using this soft barycentric refinement. And now we can look at what happens when we iterate that. We can look at the same story here in the case when we iterate this soft barycentric refinement, especially in 2 dimensions. In 2 dimensions, the vertex degree does not increase. So most of the vertices, when you do take a polyhedron, 2-dimensional polyhedron, or you can take a torus, then you can refine it, and you have most of the points have 0 curvature, which is really nice. In the limit, what you essentially get closer and closer to that, to the infinite plane, hexagonal flat plane, right, where every vertex has 6 neighbors. It's the nice tessellation of the plane, and what happens is, and that's what I saw experimentally, when you do you compute the density of states. Density of states is the kind of the law, right? The law of the, in the limit, right? In the central limit theorem, you get the Gaussian law. Here we get some interesting laws like the arcsin distribution in 1 dimension. In 2 dimensions, we don't know because there are gaps and there's Cantor type set. Here we don't get anything Cantor-like in 2 dimensions because the vertex degree stays bounded. That's really nice. And then I see here this, I cannot prove that yet, this piecewise linear density, probability density. This is a probability density, right, in the limit when you take the hexagonal lattice, the flat lattice, infinite lattice, like the discrete complex plane, if you want. And what is also interesting, and I'm kind of also interested in the connection Laplacian. The connection Laplacian, just because the vertex degrees don't increase, has a gap. So there's a stability of the vacuum in this infinite plane. Another story which actually started also and around 2016, which is this connection Laplacian story, where we have Laplacians which have bounded inverses in the infinite case also, which is really, really, really exciting. And that's it for today.